Let's work through an example and try to put some hard numbers to the discussion that we are having. Let's say that R1 and R2 are jointly normal, and we allow a dependence between them, and the correlation coefficient is a very useful way of introducing dependence, especially between two joint normal random variables. So that's what we have done here. Mu1 is the mean of R1, mu2 is the mean of R2, sigma 1 squared and sigma 2 squared are the respective variances, and rho is the correlation coefficient. What we'll do is we will let rho vary over its entire range, -1 to +1, and see what sort of conclusions we can draw, and what sort of situations different values of rho or different ranges of rho correspond to. In particular, let's say we take the mean as 10 for each of them, for each R1 and R2, so they are identically distributed, and each standard deviation is 2, so R1 and R2 are identically distributed, but they are dependent, as I just mentioned. Now, if I look at the joint probability of R1 less than P or R2 less than P, which is our definition of failure probability, series failure probability. So that's what you see on your screen. I have taken 4 different values of the load. So the load, as we mentioned, is non-random at this point. So I start with the load set equal to the mean of the individual elements, mean strength of the individual elements, the mean minus 1 standard deviation, the mean minus 2 standard deviations, and finally the mean minus 3 standard deviations. So that's what you see. The top line, the purple line, corresponds to the case where the load equals the individual mean values. And then at the very bottom, the blue line corresponds to the load equal to mean minus 3 standard deviations. So that is, it starts with 10 and then 8, 6 and 4. So 4 units is the smallest value of the load taken, which is the blue line. So you see the entire range of rho on the x-axis starts with -1, full negative dependence, and ends with 1, which is full positive dependence. And in the middle, rho 0, which for joint normal is equivalent to saying that they are independent. So we go through the entire range. Now, what is interesting is that on a log scale for the y-axis, you see there is huge variability, or the huge effect on the value of the load, which should be expected. So when the load is quite high, equal to the mean of each element strength, the failure probability practically starts at 1 and then drops off to something like 0.5 with increasing rho. For a lower value of load, the failure probability starts at something like 0.3 and then falls to something like 0.18 or 19. And we see the same kind of trend for the other two curves. As P decreases, P is m-2s and then m-3s, we see that it starts at the highest value in the entire range and then monotonically decreases to the lowest value when rho is equal to 1. So what can we conclude from this sort of behavior? When rho is -1, it is kind of the same thing as saying that they have negative dependence, and if R1 is low, then R2 is high. If R1 is very low, then R2 is likely to be very high. It's very unlikely that both would take high values or low values together if the rho is near about -1. So that is what we refer to as negative dependence in the previous slide. So when that happens, we have the highest possible value of failure probability. On the other hand, if we say that R1 and R2, they vary kind of together, they achieve high values together and they achieve low values together, if that happens, then PF_sys, the system failure probability, is the lowest in each case. So that kind of tells us that one has to take the assumption of high dependence or full dependence a bit carefully, because that leads to a low estimate of failure probability, and if that assumption is not right, we would be underestimating failure probability, which could be dangerous. And somewhere in between these two extreme limits, we have partial dependence, or even possibly no dependence when rho is equal to 0, and thereabout we see PF_sys almost the same as what it was on the left end of the spectrum, and then it starts to fall. Now, it so happens that this range, the negative values of rho, are really not very reasonable or difficult to defend in some sense for strengths. So if R1 and R2 are member strengths, and these members are supposed to behave the same way, we are talking about the same mode of failure, tensile failure, and they are presumably made of the same material, coming out of the same batch, may have been fabricated in the same facility. So it's quite difficult to defend the assumption or the claim that the strengths are negatively correlated. So we typically do not go there. It's a very uncommon assumption to take negative values of rho between the strengths. So we kind of limit our pessimism to rho of 0. So although technically speaking we could go for rho -1, but as I said, no dependence, if we do not know anything else about the two random variables here, would be the most pessimistic, the most conservative situation. And why conservative? Because, as you see, in each case, rho equals 0 gives rise to the highest possible value of PF_sys in each of these cases compared to all other values of rho. So if we do not know, or if we want to simplify matters, for a series system, it will not hurt to have an independent assumption between different strength variables, provided we are talking about the same sort of failure mode. Now, obviously, this conclusion is not guaranteed for other configurations, parallel systems, for example, and in fact, we'll see that depending on material behavior, we are not going to be able to say something like this. So we have to be very careful about what sort of assumption we are making. Now, let's just, before we go to the next slide, let's just remember this particular number that I just circled, when rho is 0.5 and when p is m minus 2s, so for that brown line, we have a value of the series system failure probability as something like 0.04. We are going to now look at the next question that we had: what if p is random? And so that's what I want us to remember, that the PF cis is about 0.04, and we'll see how that changes for rho equals 0.5, how that changes when we include randomness in the load.